Calculating the capacity of electron subshells. This is going to test you again on your NL notation. So remember, NL or subshell notation uses the number for N and the letter designation for L, which tells you what subshell you're in. So remember the possible values of L. If I can use my typey thing, L can go from 0 up to N minus 1. And the letter designations for L are 0 is S, 1 is P, 2 is D, and 3 is F. If you got to L equals 4, it would then just go through the alphabet. So L equals 4 would be G, L equals 5 would be H, but actually you don't really ever need to use that for ground state configuration of elements. Okay, so then you also have to recognize what the rules are for ML, and ML goes between minus L, all integer values, ... through 0, all integer values up to plus L. Okay, so depending on the value of ML, depending how many numbers that you have for that possible for ML will tell you how many degenerate orbitals you have for a particular subshell. Okay, so remember, degenerate means the same energy. It's sometimes called like multiplicity, like the number of orbitals you have within a subshell. All right, so we've got the 4F subshell, so that means N equals 4, and the F designation tells us L equals 3. So now we have the L designation, we can work out what the possible values for ML are. So for 4F, ML could go between minus L and plus L. So if L is 3, that means it can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So that is 1, 2, 3, 4, 5, 6, 7 F orbitals. And that's the same whenever L equals, I can't even type, whenever L equals 3, you will always have 7 orbitals, okay? So how many electrons can you fit in an orbital? Well, you can fit 2 electrons in each orbital, one spin up, one spin down, so 2 times 7 is 14. So the maximum number of maximum number of electrons you can have in any F orbital, whether it's the 4F, the 5F, would be 14. Sorry, I need the coffee. All right, so going on to the 3D then, N equals 3. Subshell designation D tells us that L must equal 2. So then you can work out your values of ML. So for the 3D, ML can go between minus L and plus L, so that's minus 2, minus 1, 0, 1, 2. So there's 1, 2, 3, 4, 5 d orbitals. Okay, so that's the same as if it's 3D, 4D, 5D, there will always be 5 degenerate d orbitals. So 5 orbitals, each of them can hold 2 electrons. That means there's a total of 10 electrons in the 3D subshell. All right, and then finally the 2s. So N equals 2. S designation tells us L equals 0. So the only possible value of ML is 0. Going from minus L to plus L, okay, 0. So there is 1 s orbital. Same goes if it's 1s, 2s, 3s, 4s, blah, 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 blah. So one single s orbital can hold up to 2 electrons. That's it, okay? Just saying, we had another one, like, I don't know, let's make it fun. The 3p, why not? So that'd be N equals 3, and then L equals 1. So the possible values of ML for 3p, ML can be minus 1, 0, or plus 1. So there's 3 values of ML, so there's 3 p orbitals. So that's the degenerate p orbitals. So each one of those p orbitals could have 2 electrons in, so there's 6 total electrons that you can have in any 3p designated subshell. Okay, so those are the only numbers you need to know. Like, there's only S, P, D, and F that we're going to use realistically. And you get 2 electrons per orbital. So that's it. As long as you know how many orbitals you have per subshell, you know how many electrons that you can have as a maximum in a subshell.